Welcome. In today's video, we're going to talk about the second model that we can use to explain electron behaviors as we make our way through Chapter 9. So in this segment, we're going to focus on what's known as the quantum mechanical model of the atom. And so this replaced what we talked about last time as the Bohr model in the early 20th century. Now, one of the key differences here is that in the quantum mechanical model, the Bohr orbits, right, the circles that showed where electrons could exist, are replaced with what are now called quantum mechanical orbitals, which we will talk more in detail about as we go through this video. So quantum mechanics, or the development of quantum mechanics, revolutionized physics and chemistry. So this is the first sort of basic one that we want to understand. So this is a big field, right? So what we're thinking about here is just one little aspect or one use of quantum mechanics, and that is to explain how electrons function or how electrons exist in an atom. So in this quantum mechanical model, electrons do not behave like particles flying through space. So we imagine electrons as these tiny particles, have some mass but very low mass, and we think of them as just these particles floating through or moving through the area outside the atom. But that's not really how they exist. It turns out that these very small particles, what we call quantum particles, so we're focused on electrons, but these same aspects would occur to other very small particles as well, what we call quantum mechanics. They function under a different set of rules, what we call quantum mechanics, as opposed to normal mechanics, right, which govern the rules or govern the behavior of larger particles. So first of all, these electrons do not behave like particles when they're flying through space or when they're moving through space, right? As a result, we cannot in general describe their path, right? We can't trace, oh, they started here, they end up here, right? So we can't in general know the path that they travel. Now, a quantum mechanical orbital, right, is a 3D probability map. So in the Bohr model, we had these orbits, right, which sort of envisioned, like we think about planets orbiting the sun, right? In a quantum mechanical model, it's a little bit more complex, and these orbits are replaced by what we call orbitals, which are 3D probability maps. Now, what these probability maps show is they show where an electron of a given energy or other properties is likely to be found if you were to look for it, right? If the atom were to be probed to try to find the location of this electron, what the orbital shows is a map, if you will, of the area which would have the highest probability of having that particular electron in it. It does not represent the exact path that the electron takes, right? So it doesn't like move, all over the orbit. The orbital doesn't follow a specific pathway, but the orbital represents the general area of space where that particular electron has the highest probability of being found. So if we use baseball and strike zone here as sort of an analogy, right? So the first idea is when we're pitching things or throwing things like a baseball, right, those large particles operate under what we call classical mechanics, right? So we can predict, right? It's predictive, right? If we calculate the forces acting upon that baseball, how it's thrown, how fast it's thrown, etc., we can predict with a high level of certainty, right, where that ball is going to end up, right? Where it's going to cross the strike zone, where it's going to cross the plate, where it's going to end up, where the catcher would catch it, right? Because we have lots of equations and something, we can predict that if we know the forces acting upon it. However, if we were pitching quantum particles, right, we cannot predict their path, right? they don't function that way. And so in a quantum mechanical world, the catcher would not know the exact location, right? Or we couldn't predict the exact location where the electron would cross the plate, where it would be at that particular time. So if we had a camera that could take the picture of electrons as we pitched them or threw them across the plate, right? And we could capture where they crossed the plate, you could see this kind of setup, right? Where they're not going to cross the same place twice necessarily, but we could track where they do, and we would start to notice patterns, right? We'd start to notice areas of higher probability. And that's the idea behind these orbitals or these probability maps, right? We could define an area that would tell us that within this area we have a 70% chance of capturing where the electron's going to be, etc. And so as we go to get more and more certainty, if we want a higher and higher percentage, then we're going to have to create a larger area, is the idea. And so that's what orbitals represent. They represent, to some level of confidence, where the electron is likely to be found, right? In what area of space. So that's the idea between these probability maps. Now, what that goes along with, and what we mentioned at the very beginning, right, of this chapter, is that like the photons of light that we saw, like light waves, electrons exhibit this wave-particle duality. Right? So, when they're moving like this, they move as a wave moves, right? Now, of course, they do also have particle properties, right? They have mass. We can measure that mass. So, but just like a wave, or just like a light wave, right? We can't know both things simultaneously. So, we have some properties that we can measure the particle nature, some particles we can measure the wave nature. So quantum particles exhibit this same kind of duality as what we saw in electromagnetic waves. Now, how do we identify or label or keep track of these orbitals, right? These areas where the electrons are likely to be. Well, in the quantum mechanical model, we use a number-letter system to specify an orbital. So the lowest energy orbital in the quantum mechanical model is called the 1s orbital, right? So it's labeled by the 1, right, and the s. Now the 1, or the number in general, is called the principal quantum number, sometimes abbreviated with n, and it specifies the level or shell of that orbital. So in other words, how close it is to the nucleus. So we might think of this as sort of in line with Bohr's levels, right? He had, level 1 close to the nucleus, level 2, 3, 4, and as the number gets bigger, right, we get further away from the nucleus. So we can see a 1, right, is going to represent an area that's going to be close to the nucleus. Therefore, lower in energy. So the higher the principal quantum number, the higher the energy of that particular orbital or set of orbitals. And we use the same integer values that we used in the Bohr model to identify these, right? 1, 2, 3, 4, etc. Now, the letter indicates the shape, or what's sometimes called the subshell of the orbital. So the possible letters that we'll see are S, P, D, and F. And each one of these indicates an orbital of a particular type of shape. Now, for example, we saw the 1s orbital. So orbitals that have an S connotation are spherical in shape. So if we look at a picture here, the 1s orbital might be represented something like this. Now, there's different ways to represent orbitals. We can represent them as sort of solid geometric shapes, which is often how we picture them, right? They can be representing as sort of those strike zone ideas with all the dots, right? That would be, if we were to take this dot diagram, right, that represents the probability of finding the electron in that particular area. So we can see in the 1s, right, the dots are closer together here, closer to the nucleus. So we got higher concentration, more likely to find the electron there than where the dots become less frequent out here, right? And typically we use the solid structure, and what we understand is that within this solid structure, right, is that probability map, right? And so this represents the area which, say, 90% of the time the electron would exist, and within that area there's certain areas that the electron is more likely to be found. Now, we don't get into that level of detail here, but we just want to be able to recognize the shape that goes along with these different letters. Now, as we go further away, so to a 2, let's say, so we go from the first shell to the second shell, there is a second or another s orbital, right? So every shell, every level has an s orbital, right? And they're all spherical shaped. So what's the difference? Well, essentially the difference is the size. So since in the second level the electrons are more likely to be further away from the nucleus, we have a bigger area to encompass where the electron is likely to be found. So it's kind of like these sort of stacking ideas, right? There's a 1s orbital that's a certain size. There's a 2s orbital, same shape, bigger. 3s orbital, same shape, even bigger, right? Because the electrons have higher probabilities of being found further away, so the shape must be larger to encompass that. Now, other types of orbitals. Now, what we'll see is these orbitals not only have different shapes, they represent different numbers of orbitals. So in an s orbital, in an s level, or excuse me, an s sublevel, there is one orbital, the spherical. In a p subshell, right, or a p set of orbitals is represented by a set of 3 maps, 3 orbitals, 3 individual orbitals, each of the same shape, but oriented in different areas of space. So for the p orbitals, we have 3 what are sometimes called peanut-shaped orbitals to go along with the p. That helps me remember it. All right, where we have these 2 lobes, and we have one that is in the x-axis, one that's in the y, and one that's in the z. And together, these make up a set of 3 p orbitals. And when we have p orbitals, they will always exist as this set of 3. And then we have d orbitals, right? D orbitals are going to be mostly what we call 4-lobed orbitals, right? So you notice most of these, except for this one outlier here, has 4 lobes. Now, just like the p orbitals always come in a set of 3, the d orbitals always come in a set of 5. So as we go through this and we talk about s orbitals, p orbitals, d orbitals, we always want to remember that when we say we have an s subshell, that's 1 orbital, right? When we have a p subshell, that's a set of 3 orbitals. When we have a d subshell, that's a set of 5 orbitals. Now, if we kind of put all this together in one picture, we see what's going on here. So, if we're on the first shell, right, then equals 1, close to the nucleus, we have only an s orbital in this area around the nucleus. Right? We're limited in space. Right? As we move further away from the nucleus, right, we have that 2s orbital, right, but we also have a set of p orbitals that can exist at generally this distance from the nucleus. As we move further away, we now bring in d orbitals that can exist. As we move even further away, we bring in f orbitals. Now, at this point, we don't care about the shape of f orbitals. They're more complex in shape, but what we do want to understand is they always exist as a set of 7. So, remember, we have a set of 1 for the s, a set of 3 now for the p, a set of 5 for the d, and a set of 7 for the s. So we can see the pattern, right? 1, 3, 5, 7, right? And once you get beyond the 4th shell, we have these same 4 subshells each time. So if we kind of summarize here and look at the comparison between the Bohr model and the quantum mechanical model, right? So in our quantum mechanical model, electrons are excited, they jump to a higher energy orbit, they release energy when they relax to give the line emission spectrum now. This can be shown by both models, right, equally well. The only difference is in the Bohr model, we're looking at relaxations and excitation between orbits. In the quantum mechanical model, we're looking at relaxations, excitements between orbitals. But both of them do a good job of explaining the line emission spectrum. Now, unlike the Bohr model, the quantum mechanical model can predict these line spectrums for not only hydrogen, but many other multi-electron elements as well. Now, the orbitals are always occupied in the same order, right? So electrons will always want to be at the lowest energy possible. So you will always see that the 1s orbital, or the lowest energy orbital, is always occupied first. Then we move up to the second level, and we have the 2s and the 2p orbitals, etc. Right? And so we go in energy order, right? So when we move on and we start putting electrons into these orbitals, or visualizing how the electrons would be in these orbitals, we always want to start with the lowest energy orbital and then move up.